want to say on canonical quantization. And tomorrow we start talking about path integral, okay? So don't hesitate also to use the homework one when I ask about comments or anything. If you are interested in something in particular, I can still try to adapt depending if it's not totally out of what I'm planning to do. So you can use that, okay? And so what did we do yesterday? So yesterday the idea was to start from, can we start from classical mechanics and change maybe one of the assumptions of classical mechanics to almost get to all these axioms. And so indeed, yesterday we changed that maybe observables now are not number-valued function, but should be linear map or matrices. And just changing that was then implying that we don't have commutativity between them anymore. And so we showed that indeed then the Poisson bracket, using the axiomatic definition of Poisson bracket, that we could go to now commutator, okay? So between now classical quantity. So here, and we also, because of the reality condition, we showed that indeed the physical quantity now is going to be an Hermitian operator, okay? So we had that. We mainly arrived also here that the Poisson bracket in classical mechanics now is going to be replaced by a commutator. And we've seen that indeed, if we only work with operators, at some point we want to go back to the notion of when we measure something, we're going to get a number, a real number, and for that we introduce that indeed we need to introduce a vector into the game. And we more or less obtain that indeed from an operator you can get a number, a real number, doing this combination, which is exactly what you call the expectation value of the, when you measure, when you do some measurement. Okay, so the idea of yesterday was really starting from Hamiltonian mechanics. What can we change to go to this, okay? And so maybe at the end of the lecture, I had some question about, so in the literature, if you look at the axioms of quantum mechanics, you find many versions, okay? And so what does it mean? Why are there many versions and this kind of thing? So what are these axioms first, maybe? So you remember we started, so this is really kind of Dirac's approach. So the idea of Dirac was, we know that quantum mechanics should be still close enough to classical physics, classical mechanics, quantum mechanics should be close enough to, but we want to introduce this H, so how can we, this Planck constant, so how can we proceed? And you figure out that starting from the Hamiltonian formulation, you can have something quite similar, and you end up with these axioms. But so these are not like kind of the more modern vision of quantum mechanics, okay? If you remember what Rob told you the first day, is that quantum mechanics is still evolving the way we describe it, and in particular, the way the axioms that we consider as sufficient are really evolving. And these are not maybe what I would call the minimal set of axioms. And already, we talked already that if you deal with vectors like this and not with density metrics, some of the problems won't be able to be treated, okay? So you can see that this kind of framework has some limitation already. And already at the, and you're going to see in the second part of the course, when you're going to talk more about these generalized axioms, that in fact maybe some of these points can be written in a bit different way or without exactly the same interpretation, and that it's going to allow you to work in a more general framework or this kind of thing. But already at the classical level, I just wanted to say that, you remember yesterday we started, let's imagine that we are a physicist at the end of the 19th century. We know classical mechanics mainly using Newton's equation, can we go from Newton's equation to something to what is called quantum mechanics? And of course, you haven't spent so much time thinking about that, but many physicists did it before you. And there is no way really to relate Newton's mechanics to quantum mechanics. And we had to go to another level of abstraction, meaning that to the Hamiltonian formulation, okay? And so Newton's mechanics, you start with a differential equation. Hamiltonian, you start from an Hamiltonian, and you derive the differential equation from that, okay? So you have another level of abstraction. But already at the classical level, you could start, instead of starting Hamiltonian or an action, which is, you could also say, now I'm considering the symmetry of my system, okay? And from symmetry principle, in fact, you could also derive the action. And we could also use this kind of picture to go to quantum. And this was one of the questions at the end of the course. In the reference I gave you on the wiki, there is a book by Valentin, and if you look at the derivation of the axiom, what are the axioms he has, and the way where they come from, it's really more from symmetry arguments. Okay, so it's a kind of other level of abstraction, and then so I would say that the picture in this book is a bit maybe more modern than the one here, and it's closer than what, for example, people in quantum information or in foundation are using, okay? And so the other question was also, if now I'm working in quantum information, so this I think is maybe a reference that Aggie is going to add to you. A very good book is going to be the one by Nilsson and Chang. And again, as we said at the beginning of this course, we are going to give you different frameworks. And for each of these frameworks, so this is more going to be for quantum information point of view. All of these frameworks, there is a slight difference maybe in the axioms you start with. But this is also a bit it's not so easy to make connection with all of them. Usually some are, from my point of view, some are more general than the other. And so it's a bit part of your work also to, if you're really interested in one aspect, to try to connect and understand why is it different and why you don't need all that, and or maybe why you really need to go to this generalized axiom to treat some of the problems, okay? So for what we're going to do and to introduce the path integral formalism, these axioms are okay, so I'm going to work with that. And it's come from, the Dirac framework. Okay, so this is just one point I wanted to do. So now, so these are the axioms you also add in the tutorial. Maybe I just want to spend some time on this expression just to see in practice how you interpret, because you see how can you relate this one, to the A2, which is telling you that when A is measured, the result is going to be one of the eigenvalue, okay? So how do we go from here to here? So let's maybe just consider quickly two cases. The first case is where A has discrete eigenvalue. And then the second case will be, of course, when A has some continuum eigenvalue, okay? So let's call AN. And you have shown in the first day for the homework that when A is Hermitian, then for distinct eigenvalue, then the eigenvector are going to be orthogonal, okay? So here we can, of course, choose as a basis some associated eigenvector, and we can choose them as an orthonormal basis. So this means that here we have and then delta NM, okay? And so now I'm going to choose here to compute the expectation value, we choose an arbitrary vector that can be decomposed on this basis. Okay, and so now if I wrote you can check that let's maybe keep this notation. Here you're going to get that this is going to be given by A n okay, so just expanding, computing this object. So here, yeah, let's choose also that we choose a normalized vector. Okay, so in this case we get that. So now if we go back to axiom 2, it tells you that the result of a measurement of A in state n is always going to be an. Okay, so what does it mean here? How do we interpret this? This means that now the probability of the outcome of the measurement being an, okay, is going to be given by this. And so this number is just what we call the probability amplitude. Or the weight of the state n in this vector. Okay, it can be also interpreted like this. Okay, so here and now, if we work with A having a continuum spectrum, then we're going to use the Dirac approach. Okay, so we're going to consider that in fact we extend our Hilbert space to allow to have this kind of object. So as now okay, so in this case, the state can be decomposed on where here we use as a resolution of the identity. So this is what is allowed in this Dirac approach, is to have this kind of okay, so in this case, this abstract vector can be written like this. And of course, this is going to imply the normalization, the continuum normalization between two eigenvectors given by now this delta function. Okay, it's a Dirac delta function. So how do we? So let's now expand this object. So here, this was the result for the in the case of a discrete eigenvalue. Okay, so now we want to, and so this is defined as the expansion coefficient. So now we also consider that the vector is normalized. So the identity can also be written as we just write the normalization. Sorry. So the normalization implies and so from this, we can just deduce the expectation value of the observable A for this vector psi is given by A Okay, and so of course I cannot move this blackboard, so I'm just going to give. So, which means that now the probability with which the measured value of A is found in the interval A plus D. So, in this interval, so probability for which the value of A is in this interval is given by, so this is the probability, and we call the probability density. Okay, so now if we consider just, this is called a probability density. Sorry, so here is a dA, otherwise I'm already talking about the density. So now the probability density is just given by, which is just this part, okay? So here we have two different, sorry. So the probability of, for which the measurement of the, is going to be the value of A in this interval is given by this number. And here we have what we call a probability density. Okay, so these are the two distinctions when you work with an observable with discrete eigenvalue or continuum spectrum. Okay, so these are just the way more or less you relate these two axioms, and these are just the very few things I wanted to say about that. So, is there any question here? I guess this is here to, yeah.
I wonder if we need a fifth axiom with the collapse of the wave function. If that can be handled in another way. That the measurement collapse the wave function.
Yeah, so it's a good point, and depending again where you go, you some people say you need to add it, and I think it's maybe something we can. I can come back on that later on if you want, about, or maybe in the tutorial we can try to have a discussion about all these axioms and comparing, or maybe once Aggie would have given her own axiom, maybe we can organize a session where we compare and try to see why sometimes you add an axiom, why sometimes you don't consider you don't need an axiom, and have this kind of discussion.
So we don't need it extra.
No. Yeah. So most of, so this is really, coming from this Dirac framework. These are really the axioms that you have, but then there are some. We can come back on that. Good question. Thanks. Okay. So let me. Okay, so to finish, what I want to introduce is a really important operator, because we're going to see that, in fact, indeed, the path integral formalism is going to be based on this operator. Okay, and just say a few words on the different picture of time evolution that I think you're already familiar with, but just to make sure that this is clear. And of course, then to go from this formalism to the path integral formalism. So as I said, the central object is going to be the time evolution operator, but in a representation, okay? And so here we're going to come back to what you should be quite familiar with. So the position representation and the momentum representation, and talk about wave function and how to do some calculation between the two, okay? So let's start with, maybe before giving you what is the time evolution operator, let's start again from, so this is the second part. And I'm going to start again from the Heisenberg equation because, so we solved the Heisenberg equation for a very simple example using a specific representation, but in fact you can have a kind of abstract solution to that, and the solution is of course given in terms of the time evolution operator. Okay, so it's a good way to introduce it. So let's go back to this equation for a given operator. And we're going to discuss about this formal solution, which is given by is the I correct? Yeah, I guess so. In the case, so here the formal solution. But it's valid in the case of time independent Hamiltonian. And these two operators are related by what we said unitary equivalent, because they are related by a unitary operator, which is this time evolution operator. Okay, so u of t here is with a minus. And this is what we call the time evolution operator. But again, this solution is when we have a time independent Hamiltonian, but the time evolution operator is, we can define it for any kind of Hamiltonian. And so now let's talk about this time evolution operator. And I've seen that for the homework question for today, most of you know how to define it. So it's going to be, so u of t is in general the solution of the equation and usually we need to, it's a differential equation, so we need one initial condition where we're going to choose that at initial time, so we choose the identity. And so from what I've seen, most of you know the definition. What is the general solution here of this differential equation? It's given where I'm going to use this t to denote the time ordering operator. And why this is necessary, it's because, of course, so here, in this case, you see that you have an exponential of an operator, but if now h depends on t, h of t1 and h of t2 are not going to be commuting operators anymore when they're evaluated at different points. So you need to, this means that you need to specify the order you're using, okay? And so here, it's just going to be given where here we're going to use the, so usually we choose an order, so by convention I'm using the right to left ordering. And here it's the ordering of a sequence of Hamiltonian at different t. Okay. Let me maybe move that you can see. Okay, so this is just the general, the way the time evolution operator is defined as being the solution of this equation. Okay, and this is the general solution. And of course, if now h does not depend explicitly on t, then you recover directly this the previous equation. Okay, so this is something I ask you to write explicitly in the homework. So I'm not going to spend more time on that. I'm rather going now to check with you what you know about the different picture of time evolution. So this is still inside the same topic. So right here, what kind of formalism are we using?
Isomers.
Sorry?
Isomers?
Yeah, okay, so Heisenberg is when the operator depends on, so it's the Heisenberg picture, so the operators now depend on time, but the states do not, okay? So as soon each time when I wrote a state here in this calculation, it was independent of time. So this is indeed, right now, it's the Heisenberg picture. So and so what is the other equivalent picture that we have?
Schrödinger's picture and Dirac.
Yeah, Schrödinger. So in Schrödinger, it's going to be, so now this means that you have operator dependent t and state do not. And an equivalent picture is going to be the Schrödinger picture. So now in Schrödinger picture, the states are going to depend on t, and the operator won't, okay? So we're going to start again from the expectation value like we consider here, where everything is written in terms in the Heisenberg picture, and go to the Schrödinger picture, and then I just want to check something if this is clear or not with you. So it's going to be quick. So let's start. So the idea is to go from Heisenberg to Schrödinger. So let's start from this that can be, so the idea now is that I'm going to use the unitary operator to introduce A0 at T0, okay? So let's now consider that T0 is 0 for simplicity. A0 so you see that now, instead of considering that this is acting on this, I can introduce kind of this bracket. Okay, and indeed, this is going to give me a definition of a state depending on time. Well, here, so I just choose the and then, of course, you can, once you have this, you can expect the expectation value in terms more in the Schrödinger picture, okay? So this was easy, and I think you already did that several times. But now let's recover just the Schrödinger equation. Okay, so I'm going to use, and so since right now we are working from one picture to the other, to make sure that everything is clear, I'm going to use a subscript S or H, depending if an object is in the Schrödinger or Hamiltonian picture, okay? So these things can be, if I add my subscript, explicitly means that here I'm in the Schrödinger picture, then I have this operator, and this state is in the Hamiltonian picture, okay? So now the question is, how do you get the Schrödinger equation for this state? So how do you get just the Schrödinger equation here? Oh, and I'm missing. Get H bar.
Differentiate with respect to time.
Yeah, it's okay. So it's very simple. You just differentiate both sides with respect to t, and you get the well-known equation. And okay, so I just differentiate both sides. Okay, very good. But two things. So first here, I wrote everything using this simple case where H is independent of time, okay? And then on the H, I didn't put any subscript. So is it supposed to be, what is it here? It doesn't matter? Why it doesn't matter? Because, for example, if now I start from, so H, I did that. So let's start again from the time evolution equation, okay? So if now I start again, because here I was in this specific case where H is independent of time. So here I have this equation. Is that the case? Yeah. And I'm going to add this. So this is just identity, okay? It's a unitary operator. So this, by definition, is identity. And all this depend on t. And H can also depend on t. And now I can apply the state on both sides, okay? So what do I get now? Well, of course, this is independent of time, so this can be exactly rewritten as, by definition, it's going to be the Schrödinger, the time-dependent vector. So this is just dependent. And now on this side, what do I get? I get this H U of t, and then okay, is that clear? So again, this is now indeed the Schrödinger equation for this time-dependent vector, where, because H here from the beginning we are in the Hamilton, in the Heisenberg picture. So H should be H, okay? So here this means that when I just wrote that, it's more or less H, okay? And I want something in the Schrödinger picture. So if I do that now, what seems to be is that this is maybe, is indeed what should be called H of S. But you're right, it doesn't matter, okay? because usually what is that? So, and if it matters, it's really an issue because usually what is the interest going from the Heisenberg picture to the Schrödinger picture is that in the Heisenberg picture, if you want to solve an equation, you have to derive this time evolution operator. Okay, so you have to work with an operator. But the idea to go to the Schrödinger picture is that now you can work with the state. Okay, so it's really painful if to go to this equation, the h that you have here, you have to get it, and to get it, you have to compute the unitary operator. That is exactly what you were trying to avoid going from the Heisenberg picture to the Schrödinger picture. So why is it indeed that you won't have to do all that? And I think you seen it, so I'm just going to check that indeed everything, see why it's in fact not important, and it's formally the same operator, even if in one case the time is fixed in the x and p, and in the other one not. So let's maybe first start with a very simple example that can be just the free Hamiltonian, which is just defined. Okay, so this is my h, and now I want to go to hs that I said was u of t and so what is that? Now it's a polynomial, so it's even here just a square, so I just have to do that once. But if it's a more complicated polynomial, then I can do that. I can just introduce the identity between all these terms. So I have some t, I have some t, I have some t, and here I am in the Schrödinger, in the Heisenberg picture, so it's a p of t, okay? And so now what are these objects? Hopefully it's in the right order. Yeah, so it's going to give you just p of t0 and in fact, so what we're going, because an Hamiltonian is going to be a polynomial function of x and p, okay? So you can always do this kind of trick. So what do you get is that here, indeed, h of, and this is going to be general, so what does it mean? This means that the Schrödinger Hamiltonian is the exact same polynomial of our power series as you want in the position and momentum as the Schrödinger, as the Heisenberg Hamiltonian. But the only difference is that now the position and momentum operator in the Schrödinger Hamiltonian are frozen in the initial time. Okay, so this operator, whereas in the Hamiltonian picture, the time here is not frozen. Here it's frozen to t0. Okay, so this means that indeed you don't care. You don't need to put any subscript on this h. It doesn't have to be, because in practice it's going to be exactly the same. It's just that you know that in the Schrödinger picture, you don't want your operator to depend explicitly on time. So they want the time is frozen there, and so this is the only difference. Okay, so any question on that? So you were right. We don't care here, and you can really derive that without being really careful. It's just then the way you interpret the operator inside. Okay, the way they are written. Any questions? No. Was it clear? You knew that from the already. Okay.
In the Heisenberg picture, so the h you start with on the left here, h hat is p hat squared over 2m, just
yeah, so
hat have time dependence.
Yeah, so here it's this one, and here it's h because this is p of t. Okay. So everything we derived until now was always working in the Heisenberg picture. Now we try to go to the Schrödinger picture. So this means that this Hamiltonian evolution, the time evolution operator that I wrote is written with this h in this Heisenberg picture. So when I do this derivation, the h here is in practice the one from the Hamiltonian picture, but you have seen that in fact, normally if you do correctly the derivation, you get this, and this just mean that you just need to consider the same Hamiltonian as in the Heisenberg picture, meaning the same polynomial of x and p, polynomial function of x and p. It's just that since you're in the Schrödinger picture, none of these operators now, x and p, are time dependent explicitly. Okay? So this equation so now you can forget about making a difference. Okay? So maybe you want to take 3 minutes of break now, because then I'm going to do the next. And if you want, we can stop. Go on with that. And then I'm going to go to the representation. Okay, so representation. And wave function. So the choice of representation means that you choose the basis, okay? And the one you should be really familiar with is when you use the coordinate representation or the position representation, which is going to give you wave function. But you can also define, in fact, wave function for the momentum representation and this kind of thing. So we're just going to work a bit with all that and playing with abstract vector and this kind of thing. Okay, so the coordinate representation. So the coordinate representation, as I just said, is obtained by choosing as a basis the set of eigenvector of the position operator. Okay, so here we consider the position operator. So you can, of course, consider a position with several indices, or usually 3 if you're space. And then this can be kind of a vector. And it's going to give you. So in the rest of I'm just going to work in 1 dimension, but here there are several kind of assumptions. The first assumption is that space is continuum, okay? And also that these different operators are commuting so that they can be, so that indeed they have a common set of eigenvector, okay? And of course, the first assumption behind this result that space is continuum may have to be maybe reviewed if you want to talk about a theory of gravity, for example, to treat gravity at the quantum level. But so right now, let's keep this like this. And so you have shown in the tutorial, in the first tutorial, that the spectrum of this position operator, so until now, then I'm going to forget about the alpha, is all real number, okay? So the spectrum and the corresponding eigenvector are then going to be continuum normalized. So this means that they're going to satisfy kind of equation. Okay, so this is nothing really new here. But so now let's try to. So the first thing we want to do is starting with an arbitrary vector. Okay. We want to, of course, write it as in the position representation. So for that, we're going to introduce a resolution of the identity using this as an as a basis, okay? This eigenvector as a basis. So here the resolution of the identity is given by this, and now we are applying this on this vector. And okay, where the resolution of the identity is, okay, so here nothing really new, and so this, here I use this notation, and this is what you call the position wave function.
Next, though.
Sorry?
So
Oh, yeah. Thanks. And so this is what you use to call the position wave function. Okay? And so now, maybe, so this is a vector. Now, if I talk about an operator, can you get the spectral resolution of this? So can you expand first this operator in the position eigenbasis? So how do you get the component of this? So what would you do? Sorry? Yeah, only one, or you need two, or if now it's an operator, okay? So you're just telling me I insert identity, so I'm going to get something like this, dx x.
You need to do it from both sides.
Yeah, okay, so here what we want to do is indeed we want to do that on both sides. So I'm going to introduce identity here and here, and then I'm going to get like two integral on R. So dx prime, and I'm just going to get x where here it's what I'm going to call, usually you then use this notation as a, so this can be seen as a matrix, okay, as matrix elements with continuum indices, okay? So usually we're going to use that a lot, this kind of, especially so when we're going to go to the path integral formalism, we're going to work with the operator we're going to be interested with is going to be the time evolution operator, but again in this position basis, and so we are going to deal with matrix element that of this type. Okay, so this is short. So now let's look at the action of an operator on a position wave basis. So up to now we have defined the action of an operator on an abstract vector. Okay, so now we want to look at the action of an operator, but usually we want to write it directly on this wave function, and you're used to that because usually you're very familiar, for example, with the Schrödinger equation directly acting on this wave function, okay? But in fact, if you start from this abstract operator acting on an abstract vector, what we get is a kind of induced action. And let's see. So let's first consider maybe a specific operator, like the position operator. So and we consider a position eigenstate, which is mapped into another state. So for example, let's consider that I'm changing notation. Let's say that this is an eigenstate, which is mapped into another vector. So meaning that I have this kind of equation. So this is mapped into this vector, but I am adding another assumption is that it's an eigenstate. So this means that it has an eigenvalue that here I decall x, maybe. And so if now I go to the position representation for all these vectors, what I'm going to get is that, so this abstract vector in the position representation just comes from that you act with X on this. And this is also the same thing as saying that you're acting on this vector, but here, if in the case this is an eigenstate, you can then in addition say that this is X okay, and so usually, so then we are going to say that the action on this vector is going to be, so we're going to use this notation. So we define now the induced action. And we're going to denote it by a dot. Okay, of, so now we are going to consider fx on a wave function. And so this is defined as x acting on this wave function is give you this result. So maybe I forgot. And so this is a kind of shorthand notation, and I can now generalize this for an abstract vector. So you see here what I'm saying is that because really if there was not the point, more or less, this would mean that you can go that outside, okay, which is not the case. So here the point means that indeed you have this kind of relation you see here. So for an abstract operator A, then usually we're going to, this kind of notation is going to be the induced action of A is just given where now okay, so this is, and in fact usually we're going to, very soon you're going to forget about this dot, and you're used to this really already with the Schrödinger equation. But if you really try to start from the abstract Schrödinger equation to go to this, the one you know, in fact, the calculation is quite long if you don't use directly this kind of shorthand notation directly. Okay, so this is something you could try, is starting from the Schrödinger equation, the abstract Schrödinger equation. How do I get the Schrödinger equation for the wave as function without using this directly, this shorthand notation? Okay, this is a good exercise to do. Okay, so now any questions? So now I want to go to the momentum operator, P. Okay. And we're going to do some proof. Okay, so now it's and in particular we want to find the action of, so we have this is what we can start, and then what is going to be the induced action on a wave function. So first we want to determine what is this action, and then go to this action. So first let's introduce, I'm going to prove what is the action of that by introducing a unitary operator, U of A, which is just given. So since I'm one-dimensional, I'm not going to, it's not really a scalar product. And I'm telling you that U of A acting on first X so we're going to prove it, but first, do you have a physical argument to explain this relation? I'm going to prove it at the mathematical level, but physically, so what is this operator? What do you know about P and so what is this action? What is generating? It's generating a translation. Yeah, and you know that P is the generator of the translation symmetry in general. So, okay, so it's not something really surprising from what you should know usually, but now we can prove that explicitly. So let's maybe do the proof here. And this just follow again from the canonical commutation relation, okay? And so from that, you can deduce, if now it's P to the power N, that, so what do you get here?
Sum.
Yeah. So the sum, it's all the terms are the same. So I let you check, and really good. And time that. And so now we can look at the commutator of X with this unitary operator. And we just get, so if we expand, of course, the exponential as a sum, we just get Pn. And so what is going to be the result here? So here it's an N. So you have this here, so you can replace and then you can recompute the exponential, but what are you going to get? First, it's going to be proportional to UA. Oh, you can see it. But what is coming out? Yeah, okay. So I'll let you. And so now we can just expand this commutator and act on vector x, okay? So if we expand and add on x, we get that x, so is going to be u of a x plus a acting on x. So x is here an eigenvector of my position, so I just get x plus a. So what can I conclude now? Can I already conclude that, or what this equality is telling me? So
U of ax is also an eigenvector of x.
Yeah, very good. Okay, and the eigenvalue
Is x plus a.
Is x plus a. But so it just means right now what we have. This means that UA of x, has to be proportional to x plus a. Okay, because it's an eigenvector with eigenvalue x plus a. Then how do we get the equality here? What is the property that we should use to get the equality?
When a is equal to 0, you should get the same.
Yeah, is it like, yeah, but you have an even stronger, I guess, because here I'm not sure it's prove it for cases you want to show that for any a. So the argument here that you can use is that u is unitary, so it's easy to check that, okay? And a unitary operator is going to preserve the norm, okay, of the vector. So since U is unitary, you just and again, this result here is not surprising because here P is the generator of the translation. So now what we want is to get the action of P on X. So what is the idea? So again, this is a kind of it's a group element where the generator are given by P. So you want to get the action of your generator. So usually you go to the infinitesimal level and you expand this element, okay, to the first order. So here, what we Moment, you have a question?
I have a question about the last.
Okay, sorry.
Since we have a factor, the phase of exponential I5.
Yeah, but you don't care.
Like
No, but you get it from here. You get.
I mean the last line, the
No.
last one.
Ah, here.
Yeah. So when we use the normalization, we have like should have an exponential of I5 because like.
You mean that it's up to a phase? Yeah.
You said that if U of 0 is equal to the state itself without any phase, then you can get it to identity.
That doesn't tell you what its phase is.
Yeah, and then the phase. Yeah. So you're right that is unitary is just going to give me that up to a phase, but then it's at least for what we're doing, they're all equivalent. So right now I'm choosing. Okay. But yeah, it's a good point. And this is, again, one motivation to go to the density matrix framework is that working with vector, you will always have, it's always up to a phase, and this phase is physically not relevant. Okay, thanks for your comment. So now, to have the action of the generator, we go to the infinitesimal level. So let's do that now. So now we want the action of P. So more or less the idea is to consider U of epsilon is epsilon infinitesimal number. And we just go to the first order. So let's look at U of epsilon of X that can be expanded as, so it's 1 and then minus I epsilon HP on X. And by just what we have been proven, this is also, so this is more. And here it's an equality, so. So here it's at the first order. And so just from that, we can now extract P, and so extract P, and so what do we get? We get that P acting on X is going to be at the first order, but then we want to take the limit anyway, epsilon go to 0. Divided by epsilon. And so now, I'm confused with this. So this was not, yeah. So now I want to take the limit epsilon goes to 0. So you see that this is going to define indeed the derivative of my vector x. Okay, so this is indeed how you get that the action. The way to see. Now what do we get? So from here, so sorry, I should have changed Blackboard before, but so I'm here. And I'm going to now take the limit epsilon goes to 0, and I indeed get that the action of, so here we are looking at the action of P on X. And similarly, we can get the dual from the same thing. So this dual here is going to be acting on P, and again, you're going to get something. So I'll let you redo. And so when epsilon goes to 0, you get minus H . And so now for any state, let's look now for any state, and we're going to get, so because as I said, the first step is to look at P on X, and now we want to have the induced action on a wave function. So for any state, let's first look at any state, and then look at the X representation. So we get here that so here it's the dual action that we're using. So it's a minus I . And so this is often presented using this shorthand notation. So we get now that the action of P on a vector X is given by, derivative. Okay, so you have to be careful on this abstract vector. It's with a plus, and then you have okay, any question on that? So do I have the time? Yeah. Okay, so let's, I still want to give you the momentum representation. So this was the coordinate representation. Now we're going to look at the momentum representation, because you will need this to do some of the so now it's the momentum representation, and now the choice is of basis is to choose the eigenvector of the component of the momentum operator. So again, I'm not going to, I'm going to forget from now on this alpha. It's just going to look at something one-dimensional. And now we want to solve the previous eigenvector equation written in the momentum, okay, eigenbasis. So first, let's look at the momentum eigenvector, and we can write it using the position basis, okay? Because here, again, as soon as you have a vector, if you want to have a representation, you just insert the identity resolution. So here we choose the identity resolution in terms of the X. And this is the wave function of the momentum operator. Okay. Eigenvector, sorry. eigenvector and so now let's use what we just get, okay? So here we have the induced action of P on a wave function with an abstract vector. So now instead of an abstract vector, I'm going to consider the eigenvector of P, okay? So I'm going to act on that. So this means that I'm looking at this. And this implies, of course, that I'm just using the previous result we just derived. And here, since P, we are working with P, the eigenvector, okay? So here I'm using two different equations because this is also equal to P xp because P here is the eigenvector of the momentum operator. So here, this is also equal to that. So this is just a very simple differential equation. So what is the solution of this differential equation? What differential? Yeah. So what do you get here is that it's going to be an exponential of E I xp divided by h bar up to a normalization, okay? So this, what does it mean? First, this means that an eigenvector P here exists for each value of P real here. So again, the spectrum of P here is going to be all real number and is continuum. Like for the, here we can, okay, because this eigenvector exists for any value of P. And so now, how do we get the C here? Let's use, the question is what is C? So let's use the normalization condition here. Or maybe, yeah, so let's say xy. So, and so I want to use this to determine what is the value of C. So what should I do now? Okay, so the idea is that, of course, I want to introduce this wave function. How do I do that?
Could you put an identity?
Sorry?
I know, I thought you were asking us what to do next.
Okay, yeah, so this is my question. Yeah, so the question is, how do you now, so my point is, I want to determine what is C, the normalization here of this.
The identity in between x and...
Yeah, very good. Okay, so here you include the resolution of the identity. So you get, how do I write that? Like, P I don't know if it's really, and so now I'm using this result, okay? And so what do I get? I get that this is C star C, and then an integration of dp exponential of I p x minus y, okay, divided by h bar. And we're going to see, so now I'm giving you this result because I'm not going to prove it now, but we're going to, not today in the tutorial, but tomorrow in the tutorial, you're going to work again on complex integral. So using this result, what do you get for here? You get that this indeed is h bar Okay, and so this gives you, so of course we want to choose C. We choose C as a real variable. It's not working. So what you get here is that C is 1 over square root of 2p h bar. So I give you directly now the result of the normalized position wave function of the momentum eigenvector. And this is something you will have to use. And okay, and so just maybe to, I'm not going to give you much more. So just from this, you get directly, you can infer directly the momentum wave function of the position eigenvector. So momentum, which is quite obvious, and of the position eigenvector. Let's see, because so this is given by, and by using the Dirac notation, it's very easy because this is only exactly that. So you just get that it's the same thing. Okay, thanks. And of course, then you can use, you can express any vector in abstract vector now in the momentum eigenbasis, where you have a resolution of the identity that we already introduced here. Yeah, so it's just a choice of basis depending if you work in the X basis or in the P basis. And I recommend you to try to express, so I'm not going to do it, but just for you to do as a small exercise, and it's in the lecture note, is to express the momentum wave function in terms of the position wave function. And what you should see is that indeed both of them are related by a Fourier transform. Okay. So this is a kind of 1 or 2 line calculation that is worth doing. Just check that. Okay, thanks. So tomorrow we'll start. So first this afternoon we have a tutorial. Tomorrow we'll start the path integral formalism. Don't forget about homework 1. Thanks for all the comments. Don't hesitate to put any questions you have, because tomorrow at the beginning of the tutorial, we're going to spend a few minutes on the question if you have questions. So it's the right moment to ask your question on using the homework. Okay? Thanks for your attention. See you this afternoon at 2.